In the previous video, we applied our 4 models to the test set. And what we saw was the light GBM was performing very well. So we could have ended there and said, okay, we will just continue with the light GBM. But there's something in supervised learning called ensemble that we can use. It's used everywhere, but I'm just saying, before we move to improving the models using unsupervised, let's use ensemble in the supervised learning realm. So what we are going to do is, instead of just picking one solution, we can evaluate an ensemble or a group of models, and that might help improve our solution. So let's say we have what the principle behind this is, if we have strong ML models. Let's say we have strong ML models from different families, right? From different families. If we use ensemble, it might lead to better results. It might lead to better results than using just one of them, by itself. The reason for this is because each machine learning model, it has its own strengths and its own weakness. Let me just say, not its own learning model. Each family of machine learning models, each family has its own strengths and weaknesses. A family is something like forests or trees. Trees. We know that we know that random forest things like random forest decision trees and stuff, they're coming from the same family. They're from the same family. So those guys, we have their own strengths that are different to, let's say, logistic regression. They're different to, let's say, logistic regression. And logistic regression has its weaknesses that are different to the weaknesses of random forests. But if we put these together, the strengths of these might cancel the weaknesses of this. The strengths of logistic regression might cancel the weaknesses of the trees. That's the idea of ensembles. If all of the models are very strong, if all of them are very strong, we will probably get a very good improvement using ensemble. But if one of them, let's say the random forest, is much stronger than the logistic regression, this logistic regression is not going to contribute to the ensemble. Its impact is going to be very minimal. The result we are going to get is going to be around the performance of the random forest, because the random forest is much stronger than logistic regression. But if both of them were very strong results, the ensemble will benefit. It will result in a better prediction. So we are going to use something called stacking. Sounds scary, but it's very simple. It's very simple. Remember that we ran each model and we did CV folds, right? We did CV folds, and what we found was XGB and light GBM were very strong. They were strong models. But the problem is, these very strong models, they're coming from the same family. So which means their strengths and the weaknesses are almost similar. They're correlated. Where XGB struggles, light GB will probably struggle. Where XGB is strong, light GB will probably be strong. So we would want to introduce another strong model. The best would be to introduce another strong model that will cancel out that will at least mitigate those correlations there. So when we're using stacking, right, it is a form of ensembling. We use it to determine whether we can get an improvement in performance compared to our standalone models. When we stack, we create something called layer one predictions, and we have already done it. Remember, for our CV folds, we're keeping the predictions of the CV folds in our predict K folds data frame. So we already have those. So for logistic regression, we have that data frame for logistic regression that was keeping the predictions. For random forest, we have those. For XGBoost, we have those. And for light GBM, we have those. So those are going to be our layer one predictions. So along with our data set, what we're going to do in stacking is we have our data set like this, right? We have a data set like this, and this was maybe V28. This could have been amount and stuff like that. This is V1, this is time, whatever it was, right? Up to 28 and amount. What we are then going to do in stacking is we are going to take that data frame that was from logistic regression, and we are going to stack it here. And we take the one from random forest, and we are going to add it here. And we take the one from XGBoost, we put it there. And we take the one from light GBM and we put it there. And we are going to add them as what? As columns. So this become columns. Although they were our predictions, using here what we're going to do is we're going to add them as our columns. We're going to add them as our columns. We're going to add them as our columns like that. And then we will train via CV cross-validation on this whole data set to create what is called layer 2. We are going to create, I think it's called layer 2 if I'm not mistaken. It's going to be layer 2 predictions. So at the end here we're going to have predictions. After this CV we're going to have, in the normal process that we did for the individual CVs, we're going to have layer 2 CV. That's going to be, is it 0 or is it 1? Just like we did. So let's look at the coding there. If you go to the Jupyter notebook, you are going to see the coding for the ensemble. So basically here we see we have predictions based on, for our 4 models, we are just creating a data frame. And inside that data frame, we are going to join it to, for our logistic regression, the prediction from the logistic regression, right? How is left, and we join our prediction from the random forest, and we join our prediction from the XGBoost, and we join our prediction from light GBM. And then now what we have is a data frame that says predictions based on k-folds. For the 4 models, our columns are going to be these predictions, the ones that we added from the prediction from logistic regression, predictions from random forest, predictions from XGB, predictions from light GBM. Just like we were doing here, we're adding them with that. So this is the data set that we're talking about now. This is just the data set that we're talking about, predictions from 4 models. That is that data set. And what we're going to do with that data set is we are going to merge it to our original one. So X train with predictions is going to be our normal training set. We merge it with our one with the predictions from the layer 1 or the CVs that we performed previously, left index, and then we just maintain the indexes. You see, we just merge it on those indexes, you see. So that's pretty much what we've just done here. This was our original X train. This is the X train, and then this is the prediction of the 4 models, and then we merge them. And then we just merge them here. So now we have a bigger training set. Let me actually see if I ran it just now, because if I ran it just now, then we'll be able to look at the head of this, so you can see what the data set looks like. I don't know if I ran it or just lost memory. I'm not quite sure. Oh yes, it's still there. So you see the time V1, V2, V3, that's coming from the X train, V8 to amount. And then now we've added our prediction LR from the logistic regression. So here this is the probability of it being 1, for this record being 1 coming from logistic regression, probability of this record being 1 from logistic regression and stuff like that. This is the probability of it being 1 from the random forest for these ones here, for these records, using XGB from light GB. That's pretty much what you did. So we've created a new training set. And then here what we're going to do is, I loved light GBM previously. So we are just going to retrain light GBM using this new dataset, new bigger dataset, ensemble dataset. And we do that here, training. And then we're going to do our new cross validation again. We do cross validation again to create our layer 2 predictions. It does it for those 200 rounds again. What we're going to see, okay, cool. And then here we just run the precision recall curve and stuff like that. Precision and recall curve. If we look at the, I didn't write it here. I did write it. So yeah, if we look at the ensemble log loss now, ensemble log loss is 0.028. It's not very different from the light GBM that we already had. It is very similar to the standalone gradient boosting log loss, like our XGB or light GB. It's quite similar. Most of, I think the reason why it is because light GBM and XGB, they're coming from the same family, so they're not very, our strongest models are coming from the same family. So it's difficult for us to get any improvement because our very strongest models are correlated. Their strengths and weaknesses are correlated, so we can't really see any improvement. But this is the principle anyway. Same as when you run the precision and the recall, it's pretty much around the same area of XGB and light GB. But this was just an explanation. It was an explanation of how to do ensemble. And if you want, you can test it with maybe other models. There could be other models because sometimes you can use a tree-based one, a random forest, and a neural network, or you can use light GBM with a neural network. You can do that, and because they're coming from totally different families, and if they're strong, both of them are strong, you see an improvement in the ensemble. So this part here, we're now just selecting the model that we're going to use. Are we going to use the ensemble? I don't think so. That's just too complicated because we have to train all these other models for something that is not improving. I'd rather just straight up train a light GBM. So I'm going to just remain with the light GBM that was trained on its own cross validation, standalone cross validation, and that's the model that I will use. So we can now, you see here, we can now just plot. We can just do a scatter plot of the predictions of the light GBM by itself when you did that light GBM by itself, and you see the true label here. The true label, the zeros are the ones. You can see it's actually predicting correctly the ones. They are on this side. Most of them are on this side, and the zeros, most of them are on that side. The actual value is 0 and 1, and it's actually plotting them correctly. Of course, there's going to be noise in between. There's going to be noise, but it's very, very little. You can see that it's doing a very good job at separating the zeros and the ones. So that's it. That is it for this supervised learning project, right? We have gone from taking the data. We didn't have to clean it, but you can do the cleaning process and stuff like that. And now that we've built that credit fraud system using only supervised learning, what we will now do is we will now try to develop machine learning solutions now using unsupervised learning. That's what we are going to try to do in the next chapter. In the next set of videos, we are going to now start with dimensionality reduction. When we got this data set, it was already reduced from a high dimension that we do not know about. So we're going to see how those people did it. We are not going to use that data set, but we're going to say what was the principle that gave them those V1s, V2s, and V3s, and we'll apply it. We are going to apply it with some coding. So we'll see you in the next chapter.